back and doing all right? Okay, so no more PowerPoint. That was that. Basically, is the well, there will be like a short PowerPoint with just some formulas a little later on, but most of the rest of this will be me yakking at you guys on the board, a lot like pathophys. So, what I want to do now is I want to go back and I want to focus a little more on metabolism. Okay, because it's such an important thing. Okay, so metabolism. What is metabolism also known as? Biotransformation. Awesome. So, what did we say the general picture of biotransformation is? What's the general thing that happens?
Break down and build up.
Okay, we're breaking down, building up, and in general, what do we do to drugs when we biotransform them? We turn them into metabolites that are more polar, right? More polar. Right? We make them more polar because polar substances are easier to get rid of, eliminate. They're easier to eliminate or excrete via the urine. Okay. Biotransformation can be divided into two phases. Okay? So we have two phases of biotransformation. I have phase 1, and I have phase 2. And I will give you guys examples here in a little bit. So you have phase 1 and phase 2 reactions. In a lot of cases, what happens when I metabolize a drug is a drug will undergo a phase 1 reaction, and then it'll undergo a phase 2 reaction. But that does not necessarily have to be the case. Okay, it's not always the case. You can just have phase 1, just have phase 2. They can be independent of one another, but in a lot of cases, you'll undergo phase 1 biotransformation, and that will set you up for phase 2. Is everybody okay with that? So, in phase 1, the major thing that happens in phase 1 reactions, you add or unmask polar groups. Right? So you add or unmask polar groups on that medication as you metabolize it. So, some of those groups might include things like hydroxyl groups, OH groups. If I add a hydroxyl group, that might make something more polar, right? It may include something, a sulfhydryl group, a sulfur that's a hydrogen that's bonded to a sulfur atom. Okay, and we call those sulfhydryl groups. We may add amine groups, which are NH2. Okay. We may add carboxyl groups and make carboxylic acids, so COOH, right? COOH, carboxyl groups. All right. We may add acetyl groups as well. Okay. Acetyl groups is a COH. So these are fairly small groups, and these groups tend to be more polar. Is everybody okay with that? Does that make sense? And how we do this, the major chemical reaction involved is something known as a redox. A redox reaction. All right? Redox reaction stands for reduction, oxidation. So let's talk about reduction and oxidation because these are very common terms that are used. A reduction reaction involves, okay, it involves take away oxygen or add hydrogen. Okay. You're adding hydrogen, You're taking away oxygen. Okay.
Or.
Or. Is everybody okay there? And ultimately what's happening is electrons are being added to this. And it's reducing the charge. You can reduce the charge. Oxidation is just the opposite. You add oxygen or you take away hydrogen. Right? So you add oxygen or you take away hydrogen. Okay, those are reduction, oxidation, or what we call redox reactions. Okay, so I can either reduce the drug or I can oxidize the drug. Is everybody okay there? You don't have to know specific chemical pathways or anything like that. Okay. And the way by which we do this, there are a specific set of enzymes that are involved in redox reactions in phase 1 metabolism. And these account for 70 to 90% of all the metabolism of the drugs that we administer, so they're kind of a big deal. These are what are known as the cytochrome P450 enzymes, or CYP. Okay? Now, I dare you, okay, to go to the Hippocrates or their pharmacology guide and look up the pharmacokinetics of any drug, just any drug you can think of. You look under the pharmacokinetics, under metabolism, and there's a good chance it's going to say liver, cytochrome P450, or liver CYP. Okay? That is how important the CYP450 enzymes are. Is everybody okay there? The CYP450 enzymes, a massive super enzyme family. They are enzymes that come from the liver. Okay, they're enzymes that exist in the cytoplasm of cells. Okay, thousands of them. And they are iron-containing enzymes. They're not hemoglobin. Hemoglobin is iron-containing, but is not a CYP enzyme. So, cytochrome P450 enzymes contain iron. And iron is really good at accepting electrons, right? You can give electrons to it, and then it can pass electrons on. And we said that giving and taking atoms and moving electrons around is what goes into reduction and oxidation reactions. Everybody's okay with that? So that's why CYP enzymes, the cytochrome P450 enzymes, are so important. They allow chemical reactions to happen much more efficiently because they can shuttle hydrogens and oxygens and electrons around. And it's the iron in them that allows them to do that. Is everybody okay there? Okay, cool. So, that's how they work. Everybody okay? You're good? Okay. Now, the reason that we call them P450 enzymes is just historical. What we did when we were first studying them is we knew that they contained iron, and so we said, hey, let's expose these enzymes to carbon monoxide. And what do you suppose happened when you expose something that contains iron to carbon monoxide? Carbon monoxide binds to it, right? Just like carbon monoxide binds to hemoglobin, the iron in the hemoglobin, right? So carbon monoxide binds to the enzymes, and then what we did was we said, hey, let's shine some light through these enzymes now that they've been bound by carbon monoxide. And what we found was that those enzymes, the carbon monoxide bound enzymes, absorbed a specific wavelength of light. And the wavelength of light that the enzymes absorbed was at 450 nanometers, which is blue. They absorb blue light. So that's why we call them P450. That it's purely historical reasons. Is everybody okay there? Okay with that? All right. All right. That's phase 1. Now the phase 2 reactions, the goal of a phase 2 reaction is to add a large or more complex, okay, add a large or more complex group that's typically polar, of course, to the drug. Okay? And these reactions, or I guess I should tell you what some of those large groups are. Those large groups, and I'm going to have to pull some notes here so I get my spelling right, include things like glucuronic acid, okay, and this is known as glucuronidation. Okay, so the gluco kind of gives it away. These are large sugars. These are large sugar molecules that we're attaching to the drug. Is everybody okay with that? When I go through glucuronidation, I'm attaching a large sugar molecule. You can have sulfation. Okay, so adding large sulfur groups. And another big one is glutathione. GSH. I'll just abbreviate GSH, okay? Glucuronidation tends to be the most common reaction that occurs in phase 2. And these phase 2 are known as conjugation reactions. And conjugate just means to add a group onto something. Is everybody okay with that? So comparing phase 1 and phase 2, phase 1 is I'm adding these smaller polar groups, okay, like hydroxyls, sulfhydryls, carboxylic acids, not really large, right? Okay, and I'm doing that by redox reactions primarily. And the enzymes that I'm primarily using are the CYP450, the cytochrome P450 enzymes. Phase 2 reactions are conjugation. I'm adding large groups. These are large polar groups. They're more complex than these. Okay? And I do not use cytochrome P450 enzymes for phase 2. Bless you. I use what are called transferase enzymes. These enzymes are known as transferase. These are known as transferase enzymes. For example, one that's important, will become obvious important, is an enzyme that transfers glutathione to a drug or a drug metabolite. We'll talk about that in just a little more detail. And that's called glutathione S-transferase. And whenever you hear the term ASE, okay, that is an enzyme. Okay, and the cool thing about enzymes is they're named after what they do. So, like monoamine oxidase is an enzyme that does what? Oxidizes the monoamine part of a catecholamine, like epinephrine, right? And so monoamine oxidase would be, what do you think? Just by the name of it, you think that'd be phase 1 or phase 2?
Phase 1.
Phase 1, right? Because it is an oxidizing, right? It's oxidizing, and we said that phase 1 redox. How about that, huh? Mm-hmm. So MAO. The other enzyme that metabolizes catecholamines in the body is catechol-O-methyltransferase. What reaction do you suppose that involves?
Phase 2.
How the hell about that, huh? How crazy is that? Yeah, it's starting to come together. Okay. Starting to come together. Okay, now, there are some phase 1 enzymes that are not cytochrome P450. And the big one that I want to mention is something called ADH. And that's alcohol dehydrogenase. Obviously, it's important because it involves a phase 1 reaction in metabolizing alcohol, or ethanol in particular. Well, all the alcohols, but ethanol's something to talk about. You guys good with that?
What?
Alcohol dehydrogenase. So I'm pulling a hydrogen out of alcohol, right? And if I'm pulling a hydrogen out, I'm oxidizing, right?
And that's an enzyme?
That's an enzyme, yeah. It is not a CYP450 enzyme, though. It does not belong to that family. ADH actually contains zinc instead of iron. And it's iron that makes the CYPs what they are. They're iron-containing enzymes. ADH contains zinc, but it does the same thing. The zinc is a metal that allows things to be shuffled around.
Okay. And I'm sorry, Chris, one more time.
Yeah.
ADH stands for
ADH
what?
is alcohol dehydrogenase. Alcohol dehydrogenase. All right. Again, guys, don't worry so much about all these minute details. This is to kind of help you understand metabolism, biotransformation a little better. Okay, you guys good there? Sort of good? Okay, so what I'm going to do is I'm going to draw you guys a little picture here. So we said that the general process of biotransformation involves taking a non-polar drug and turning it into a polar metabolite, right? Alright, non-polar drug to a polar metabolite. You guys okay with that? So I'm going to start off with my drug right here. You guys okay with that? I'm going to start off with my drug. And that drug is going to go through phase 1 reactions and phase 2 reactions. You guys cool with that? So phase 1 reactions can involve oxidation or reduction. So reduction. I can oxidize it or reduce it. If I oxidize it, what am I going to do? I'm going to add oxygens to it, right? So there's my D with an oxygen. If I oxidize it even further, D may be double bonded to an oxygen. You guys okay with that? Okay, the more bonds I have with oxygen, the more oxidized that I am. If I reduce it, okay, down here, maybe I'll have drug with a hydroxyl group. Okay, there's a hydrogen there. Maybe I have a drug with a sulfhydryl group. There's a hydrogen there, right? I'm adding hydrogens. Maybe I have a drug with an NH2. I have 2 hydrogens I've added. Okay, so I'm reducing it. Everybody okay there? So I've reduced it here. I'm having these hydrogens being added. From oxidizing, I'm adding these oxygens. Okay. In general, if I oxidize something, generally the phase 2 reaction that's going to happen is going to involve glutathione. Okay. So drug plus GSH. Okay. The glutathione conjugation reaction. Down here, it can go a few different ways. I can sulfate it. Okay, so maybe I'll have my drug with SO3H, something like that. Don't memorize this, okay? This is not to be memorized. This is just to kind of show you the bigger picture of what's going on. I can add acetyl groups, what we call acetylation, drug, all right. And I can also do the most common thing, which is glucuronidation, right? I can add large glucose molecules to it, my drug, the glucose, okay? So that's the general picture of phase 1 and phase 2 biotransformation.
Do they have to go through both phases?
No. This is like, in general, the rule of thumb is this.
So they do go through both phases as a rule of thumb?
In general, they do, but some don't. And I'll give you guys some specific examples.
But basically, we're trying to make, the body is consistently trying to make everything polar so that it can be excreted.
Yes. That's ultimately what's going on. I'm going to either oxidize or reduce it, and then I'm going to add these large molecules on top of that to make it more water soluble, more polar. That's the general way things go. You guys okay with that? Okay. Okay. Again, I'm not please don't memorize this stuff, because that's really not the point of any of this at all. So what I want to do now is I want to give you guys a couple of examples of these processes. And I'm going to give you examples with medications or drugs that we run into, or commonly run into them. And it's just to show you how this works. It's not to make you memorize it, all right? You can go and get degrees in pharmacology and toxicology if you want to memorize more of this stuff. But okay, so what I'm going to do is I'm going to take you through the complete metabolism of ethanol, of alcohol. You guys are going to learn more about alcohol today than you ever thought was possible. And why not? Because who in here does not drink? Okay, so there are two of us that don't. The rest of you guys drink. This is something you chug down into your body, right? Shouldn't you know a little bit about the stuff that you throw into your body? Of course you should. Okay, so what we're going to do is we're going to start chugging ourselves some ethanol. So what's ethanol? What's the chemical structure of ethanol? Do you remember? C. Right. So it's a hydrocarbon, but I substitute one of the hydrogens with an OH, right? So it's ethane becomes ethanol. You guys cool with that? That's ethanol. Or ETOH. You guys cool with that? ETOH? Okay, so we've got ethanol here. So what's going to happen is ethanol can be metabolized in one of three ways. The major pathway involves ADH, alcohol dehydrogenase. Are you guys okay there? We talked a little bit about that enzyme. That's the major pathway. There are two smaller pathways, or what we call minor pathways. Okay, there's this guy here in the middle, and I'm going to say that this particular pathway is a P450 enzyme. Specifically, it's CYP2E1. You don't have to memorize this, okay? Please don't memorize this. CYP2E1, okay? And then the smallest, or the least noteworthy pathway involve what are known as catalase enzymes, okay? Most of the alcohol is metabolized through ADH. And interestingly enough, your body doesn't have a whole lot of ADH. Why? Because our bodies don't normally have to deal with ethanol or toxic alcohols, so we don't have a lot of this. So it's easily overwhelmed, and our elimination kinetics easily become what? Saturated, and we go into zero-order elimination. So you don't have a whole lot of this stuff here. Okay, so what's going to happen is I'm going to take this ethanol here, and I'm going to draw a new molecule. Okay, so these enzymes metabolize this into... Okay. So I have acetylated the alcohol, right? I have removed, this group has turned into this group here. So instead of an OH, I have a double bond OH, or double bond O and just a hydrogen there. Are you guys okay with that? So have I lost hydrogens? No or yes?
Yes.
Yes, I have, right?
Yes.
Right? How many hydrogens I have? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. I've lost 2 hydrogens. And have I oxidized this? Yes, because instead of a single bond to an oxygen, I have a double bond. So has this been oxidized or reduced? Oxidized. This has been oxidized. So, do you guys remember when we talked about the Krebs cycle? Mm-hmm. Guess what? Those substances that are in the Krebs cycle become really important for enzymes. And do you guys remember the NAD molecule?
Yes.
from the Krebs cycle. Guess what? You need NAD to power these enzymes. So what happens is NAD comes in, NAD plus comes in, and how many hydrogens did we lose?
2.
NAD is good at accepting hydrogens, right? Because remember, NAD from the Krebs cycle accepted hydrogens and then brought those hydrogens to electron transport? Guess what? Remember how I told you guys that it's more complicated than just the Krebs cycle, there's all this other stuff going on? This is part of all that other stuff. That NAD comes in and it collects those two hydrogens and it becomes NADH plus H. Plus a H plus. So those are my two hydrogens. They get whisked away, right? The ADH enzyme kind of collects them. The NAD comes and whisks them away, and off they go into another cycle. All right, and now I have this molecule here. This is an aldehyde group, and this is called acetylaldehyde. Okay, acetylaldehyde. You guys okay with that? Now, here's the interesting thing. In chronic alcoholics, if I am a chronic drinker, alcohol can cause enzyme induction. In particular, it can induce CYP2E1. So in somebody who drinks chronically, they have more of this enzyme. So what can they do to the alcohol?
Break it down.
They can metabolize ethanol and acetaldehyde more efficiently than someone who doesn't drink as much. So in normal people, the major pathway is ADH, but the more and more I drink, the more and more induction CYP2E1, the more I induce this enzyme, and the more prominent this particular pathway becomes. It's not ADH, it's the cytochrome, the CYP2E1 enzyme. Is that okay? Does that kind of make sense there? So I actually have induction that occurs with chronic drinking. And you run into elimination kinetics that are very different in chronic alcoholics than someone like me if I went out and went on a bender. My ability to metabolize alcohol would be very different than a chronic alcoholic's. You guys kind of okay there? Now, I need to further metabolize this. So I started off with ethanol, and I've created acetaldehyde, and acetaldehyde is a metabolite. You guys okay with that? This is a metabolite of alcohol, once I've changed it. I am going to further change this, okay, and there are 3 pathways as well. All right, the 2,1 CYP2E1 and the catalase enzymes. Okay, but instead of ADH, I have another enzyme that I need to metabolize this. It's called ALDH. That's aldehyde dehydrogenase. So alcohol dehydrogenase is removing hydrogens. What do you suppose aldehyde dehydrogenase is going to do? It's going to remove more hydrogens, right? So what I'm going to do is I'm going to go from this molecule over to this guy here. Let's see, C is double bond to an O, and then there is an O and an H. So have I reduced or oxidized my acetaldehyde? I've oxidized it, right? I have another oxygen. And have I taken hydrogen away from it?
No.
You moved it. What's that?
No, it just moved.
Not really.
Moved
No.
it around.
Not really. Yeah.
Out of the way.
But what happens is this here is called acetic acid. Acetic acid is also vinegar. And so what happens is this hydrogen, acetic acid donates its hydrogen. That becomes positively charged, and this becomes negatively charged. And is that polar?
Yes.
That's about as polar as you can get. The entire molecule, acetic acid, of course, becomes acetate. Okay? This is about as polar as you can possibly get. And you can pee this stuff off. You can pee it off. Yippee. All right. So this is an example of metabolism where did I have phase 2 occurring at all? I had no phase 2 reaction whatsoever. This is all just phase 1. It's 2 phase 1 reactions. You guys okay with that? Okay. Again, I'm not going to expect you to memorize this. I'm just showing you how this works with some common drugs. All right. So let's talk about another drug. And this is a situation where metabolism is problematic. This causes problems for us. Okay. And this involves a medication that we all know and love, and we run into it quite a bit. Okay. And I'll just kind of draw the basic structure of that molecule, NHCOC3OH. Okay, so benzene ring and this stuff. This is a medication called, what's that? Tylenol. This is acetaminophen. So I'm going to take you guys through how we metabolize acetaminophen. So there are 4 things that can happen. I can eliminate about 5% of acetaminophen in the urine, just unchanged. No metabolism at all. So I can pee off about 5% of it in its original form in the urine. Not a whole lot, is it? Okay. Okay, that's one thing. The other thing that I can do, so I'll draw these other 2 little guys here, is I can use an enzyme called UDP, glucurno, let me just write it out here. All right, glucurosulfotransferase, okay? So basically what I'm doing is I'm going to transfer a glucose molecule, not glucose, but a sugar molecule to that acetaminophen, so it's going to be C6H8O6. Okay, and then I have all that crap up on top there, right there. Okay, so here I have the sugar. So is this a phase 1 or phase 2 reaction here? Phase 2, right? I transferred, okay, I went through I transferred a large glucose, or a large carbohydrate molecule to it. So that's phase 2, okay? And I didn't even go through phase 1, did I? I just went from here to here. The other one is, let me write this out here. Okay, phenylsulfotransferase. Okay, so that transfers a sulfate group. Okay, so here I have, this is acetaminophen, OSO3, and all that crap on top. Do you think this is a 1 or 2?
1.
2.
2, right? Transferase. I'm transferring a large group to it. So it's a phase 2. Is everybody okay with that? Okay. So guess what? You're looking at about 90% of all the Tylenol metabolism occurring through those 3 pathways, more or less. That's most of your Tylenol being metabolized through phase 2, right? But guess what? These are non-toxic metabolites here. Is that really significant for us? No, we want to know why it's toxic to the liver, right? Well, there's a very minor pathway, approximately 5%. Approximately 5% of all the Tylenol is metabolized through here, and it involves a P450 enzyme, CYP450 enzyme. It involves our good friend CYP2E1, the same set of enzymes that I have here with ethanol. What's that?
Phase 1.
Yeah, oh, you already know. Yeah. This is a phase 1 reaction. So these are all phase 2 reactions. You already know this is a phase 1 reaction. So what I have at the end of the day is I have a molecule that looks like this. All right. Double bond to an O, let's see here, NCOCH3. Okay. So this is basically the same. What's really the big change that happened here? Double bond oxygen, so I removed a hydrogen here, right? You guys see that there? I removed a hydrogen. And NCOCH3, pretty much just removing hydrogens, right?
That's an oxidation.
So it's an oxidation. And of course I need, over here, I need NADPH to take that hydrogen away, right? NADP plus H2O. So remember NAD, FAD, okay? So I have NAD here, I have NAD here. It's a slightly different form of NAD, but it's still NAD that's able to take the hydrogen away. This molecule here is known as NAPQI. Okay, don't ask me to tell you to say the whole name. It's a long, convoluted name. NAPQI metabolite is highly toxic. It's a highly toxic reactive, and it reacts in the liver, and it causes extensive liver damage. If you cannot get rid of this, you're going to have a massive liver damage. The only thing we can do to metabolize this here, okay, is we need to conjugate this. So this is a phase 1. So what I've done in phase 1 is I've actually turned my Tylenol into a dangerous metabolite. Would you guys agree?
Mm-hmm.
Through a phase 1 reaction. So in this case, I need a special phase 2 reaction to occur, okay, to deactivate this NAPQI. And I need to do that through glutathione conjugation. I need to add glutathione to it to deactivate it. So I'll get something that looks kind of like this here, the hydroxyl group down there, and I have my glutathione group that hangs off there and some crap on the top. So, what happens in hepatotoxicity of this stuff? Does our body have a lot of glutathione in it?
No.
No, we don't have a lot of glutathione because we don't need it. We have, our body makes enough to deal with some of those free radicals and things like that, but we didn't evolve taking Tylenol, right? Tylenol is a pretty recent thing, or acetaminophen is a pretty recent thing. So what happens is if I overdose on Tylenol, I have glutathione depletion. I deplete my glutathione, and this toxic metabolite, this NAPQI metabolite, builds up, and then it starts reacting with the cells in your liver and starts destroying those cells. And that's how you have the hepatotoxicity. Is there an antidote for Tylenol or acetaminophen toxicity? Well, there's a molecule that acts like glutathione that can attack. What's that?
Glutamine? Glutamine?
Not glutamine or glutamate. It's actually a respiratory drug called acetylcysteine or mucimist. Smells like rotten eggs because it has sulfur groups in it. And we used to make people drink it, like grams and tens of grams of it. It was just terrible. It smelled horrible. It was rotten eggs. We actually use it in respiratory to break up mucus as a mucolytic. But now we have an injectable form. So the antidote for Tylenol is mucimist or N-acetylcysteine. And it acts like a glutathione. It can conjugate with this NAPQI and make it much less toxic. Basically, it's an antioxidant, if you will.
What's the timeline for that? If you have a girl that takes like a gigantic bottle of Tylenol and it was like 3 hours ago.
Yeah, you have 3 phases, and I'm not going to talk about it too much because we actually have a toxicology block that we'll do. But there are several phases to Tylenol toxicity. Your first phase takes a few hours. That's where you get nausea and vomiting. You don't feel well. And the second phase is about 12 hours. And that's where your liver starts failing. And then your third phase, a day or 2 is where you get your liver failure. And then the fourth phase, 4 or 5 days, where you either die or you get better.
Wow, that's
Yeah.
crazy.
Yeah. Anyway, sorry for throwing this at you guys. Please don't go home and try to memorize this stuff. Okay, I'm just giving you examples of how these enzymes work and how we can have multiple pathways occurring and multiple things occurring. And some enzymes do the same things with different drugs. That's all we're doing at this point, okay? That's all we're doing. So I'm not going to have you memorize tables or anything like that. Take a little break.